Hello everyone, today we'll be discussing the summary of limits, continuity and differentiability. So firstly, we'll be looking at fundamental theorems on limits. Let's consider the limit as x approaches a of a function f of x to be L, and the limit as x approaches a of a function g of x to be M. F of x and g of x are the same function. So the limit as x approaches a of f of x plus or minus g of x, which is basically the functions are being either added or subtracted, can be written as a sum or difference of their limits as well. And when the limit approaches a and the functions are being multiplied, the limit can be written as the product of the individual limits. Now, the limit as x approaches a of k times f of x, and k is a constant or a scalar quantity. You can take the constant outside the limit. Now we know that the value of this limit is L, so this can be written as k times of L. The limit as x approaches a of f of g of x. Now let's look at this one. The limit as x approaches a of g of x is m. So this whole thing can be written as f of m, assuming that the function f of x is defined when x equals m. Indeterminate forms. Let's say a function is not defined at a particular x. Let's say the direct substitution of that value of x results in an indeterminate form, which can be 0 by 0, infinity upon infinity, 0 times infinity, 1 to the infinity, or infinity minus infinity. These aren't actually finite or existing values. To simplify the function, we may use factorization, rationalization, or standard limits, substitutions, and expansions. Let's look at an example of factorization. So here, the limit as x approaches 1 of this function doesn't actually exist. Substituting 1 directly gives us with the indeterminate form 0 by 0. So instead, we're going to try to factorize this function so that we can find the limit as x approaches 1. Now the numerator is in the form of a cubed minus b cubed. If you can recall the formula, this can be written as a minus b times a square plus ab plus b square. Now the limit can be simplified. Now we can directly substitute the value of 1. So that gives us 1 plus 1 plus 1, and the limit is 3. Standard limits. So these are the limits that you can directly substitute in a function when you're solving for a specific limit. And I very much recommend that you memorize these. Especially this one, these we will be using quite often. All of them are very important, but these will be used more often. Let's look at a few expansions. These are very important. There's questions been asked in JEE main, so it's very important that you memorize them. Now, first expansion is a power x, and you can see that the e power x expansion can be simply just determined by substituting a value of e instead of a. So ln a becomes actually ln e, and ln e is 1, so the ln term is gone when you come to the expansion of e to the x. And you can notice that in the expansions of a power x and e power x, it starts with a 1. So how I try to remember it is like, so in the ln of 1 plus x expansion, the 1 is already inside the ln, so you don't have a 1 in the actual expansion. And next, sine is like an odd function, so you only get the odd numbers in its expansion, and cos is an even function, so you get the even powers. These are just some ways that I try to memorize. Please feel free to obviously remember them how you feel comfortable. So these are a few more limits that are useful to know. The limit as x approaches infinity of ln x by x is 0. How do we get this? Let's look at the graph. The ln x graph progresses much slower than the y equals to x graph. So as we approach infinity, value of x is much higher than the value of ln x. So when you take ln x upon x, the value is almost 0. Similarly for this one, e power x is something like this. So when you approach infinity, the value of e power x is much higher than the value of x. So once again, when you divide x by e power x, value is very much close to 0. And the same goes for these. Now it's like even if you raise ln x to the power of n, the value will still be 0, because x is increasing at a rate much higher than ln x. And similarly for x raised to the power of n divided by e power x. Another thing I want you to keep in mind, and you probably know this already, is that sin x is less than x and x is less than tan x, and it's the reverse when the functions are in inverse. So sin inverse x is greater than x and x is greater than tan inverse of x. So next is L'Hopital's rule, और ये बहुत कम आएगा. You can use it in many questions. So basically it says that the limit as x approaches a of f of x by g of x, अगर इसका indeterminate form is 0 by 0 or infinity by infinity, then the limit can be written as the limit is x approaches a of f dash of x by g dash of x. तो ये f dash और g dash क्या होते हैं? It's a differentiation of the functions f of x and g of x. And differentiation you have learned in physics. Starting में बताया होगा. So basically f dash of x is like the d dx of f of x. Next, infinity by infinity form. So if the degree of the numerator is greater than the degree of the denominator, then the limit does not exist. And if the degree of the numerator and denominator are same, then divide the coefficient of the highest powers. What does this mean? Let's take an example. The limit as x approaches infinity of this function. So if you put the infinity value, obviously it's going to be a infinity by infinity form. And we can see that the degree of the numerator is 3 and so is the degree of the denominator, same. So what we're going to do is take the highest power common. 4 x cube times 4 plus 3 by x. So I've taken x cube common, divided by, again I take x cube common, times 2 plus 1 by x squared. The limit as x approaches infinity. So these get cancelled, and here when x is approaching infinity, 1 by infinity is 0. So these become 0. And we have 4 by 2. So the limit is 2. That's what they mean by divide the coefficient of highest powers. So highest powers is what? X cube and x cube. Coefficient is 4 and 2. So that's what we did in the end. 4 divided by 2. And you get the limit. And when the degree of the numerator is less than the degree of the denominator, the limit becomes 0. Why? Okay, same logic. So next we're looking at exponential indeterminate forms. Firstly, we're looking at 0 power 0 and infinity power 0. Let's take an example. The limit as x approaches 0, x power x. So in this case, we'll be writing this limit as y equals the limit. And next we'll apply a log on both sides. And we're getting the 0 times infinity form of indeterminate thing. So this will try to convert into 0 by 0. And we know what to do when we get a 0 by 0. You apply L'Hopital's rule. Next, 1 power infinity. So when you have the limit as x approaches a of a function f of x power g of x, and substituting the value of a is giving an indeterminate form, 1 power infinity, we can simplify the limit to this: e power f of x minus 1 times g of x. Many questions can be solved this way, it's very simple. And lastly, when you have more than two infinities approaching, so look at this example. When we substitute x infinity, all of these quantities approach infinity. And you can see that this thing as a whole is in the form of infinity to the power 0, because 1 by infinity is a 0. So in this case, take 4 power x common. When you do that, you get 4 power x divided by x, so that's a 4 outside. And inside the bracket, you get 2 by 4 power infinity, 3 by 4 power infinity. So these both are fractions. And when you multiply a fraction infinite times, it approaches very closely to 0. So these both become 0, and you only have 1 left inside. So the limit becomes 4. I hope you understood that. I didn't want to write it out. Next is your sandwich theorem. So let's take, there are three functions, h of x, f of x, g of x, and f of x lies in the middle of these two. So if the limit as x approaches a of g of x is L, and the limit as x approaches of h of x is also L, and the limit as x approaches a of f of x will also be L. So the graph will kind of look like this. A of h of x and g of x. Let's say f of x is somewhere in the middle. So if both of these functions are approaching the same value at x equals a, so will f of x. Okay. And then you have built-in limits. So built-in limits is when you basically have to make cases for within the limit itself. So let's take, we have this example, the limit as x approaches infinity of a power x. So if a is greater than 1, or let's take 2 or 3 or 4. If you multiply these numbers infinite times by themselves, you will end up at infinity. So that's the first case. The second case is when the value of a lies between 0 and 1. So that's a fraction. If you multiply a fraction by itself again and again and again, we end up at 0. Well, a value very much close to 0. And the last case is when a is 1. So 1, if you multiply 1 by 1 by 1 by 1 by 1, the result will be 1. So that's the third case. That's just one example of built-in limits. Next, continuity. It's a small topic. How do you conclude that a function is continuous at a point? So we have to make sure that the left hand limit is equal to the right hand limit, and also the function is defined at that point. Only if these three conditions are satisfied. So the left hand limit, the value of the function at that point, and the right hand limit, all of these must be equal. Only then the function is continuous at that point. If the limit exists but the function doesn't actually have a value at that point, then it's not continuous. Next, reasons for discontinuity. So obviously if the limit of the left hand limit or the right hand limit does not exist, well, the function will be discontinuous. If the limit exists but the function isn't actually defined at that point, then again it's discontinuous. If the value, obviously that's the same thing I wrote. Okay, no. If the limit exists and the value of the function also exists but they aren't equal, then also it is discontinuous. Now we will look at jump of discontinuity and intermediate value theorem. So jump of discontinuity is very simple. You have your left hand limit and right hand limit, and the difference, if they aren't the same, then the difference is the jump of discontinuity. Now intermediate value theorem says that if a function f of x is continuous in the interval a to b, and f of a and f of b have opposite signs, so then the function must have crossed the x-axis at least once. So basically the function will have at least one root in the interval of a to b. That's it. That's your intermediate value theorem. Now let's look at differentiability. So a function f of x is said to be differentiable if the left hand derivative is equal to the right hand derivative. And also if a function is differentiable, then it is continuous for sure. But just because it is continuous doesn't mean it's differentiable. Why is that? So, reasons for non-differentiability. If a function isn't continuous at a point x equals a, then it can't be differentiated at that point. So that's like this graph. You can't find a particular proper slope, right? So that's what differentiation means, the slope of the function at that point. So since it's not continuous, it's not defined at that point, you can't find its differentiation. The function is continuous, but the left hand derivative is not equal to the right hand derivative. So here the function is continuous, but the slope on the left is not equal to the slope on right. You can't find its derivative at that point. Next, the function is continuous and the slope is same. The left hand derivative is equal to the right hand derivative, that is. But the derivative itself at that point is not finite. So over here you can see it's like a straight line, so it's an infinite slope. So in this case you can't differentiate that function at a. And you have a note point. If a function is differentiable, its graph must be smooth. So ऐसे break या corner नहीं होनी चाहिए. Only then you can differentiate it. Differentiability over an interval. So the function f of x is said to be differentiable over an interval a to b, closed interval a to b, if it's continuous in open interval a to b, and the right hand limit of a and the left hand derivative, that is limit ka matlab in this case, the right hand derivative of a and left hand derivative of b exist and are finite values. Only then the function is said to be continuous in the interval a to b. So lastly, we have a few note points. The first one is that if two functions f of x and g of x are differentiable at x equals to a, then f of x plus or minus g of x, their product, and f of x by g of x are all also differentiable at x equals to a. Given that g of x is not 0 at x equals to a, rather g dash of x, no, g of x is not 0 at x equals to a. Next, f of x is differentiable but g of x is not differentiable at x equals to a, then f of x plus or minus g of x is not differentiable. What about these two? We can't tell. We have to find out by multiplying or dividing the two functions. Next, f of x equals mod of x minus a is always not differentiable at x equals to a. Why is that? We can simply draw the graph. Let's take a to be here. So f of x is mod of x minus a. The graph will look like this. So you have a corner at x equals to a, so it's not differentiable at that point. Lastly, all polynomial, trigonometric, and exponential functions are differentiable in their domains. And with that, we end the summary of limits, continuity, and differentiability. Thank you.